Welcome back. The next topic is on something called exponential functions. And until this point, the types of functions that we've been working with have been polynomials, square root functions, which are called radical functions, and rational functions, which are quotients of polynomials. So top polynomial divided by bottom polynomial. And we've been working with these types of functions for taking derivatives, for domain, and for limits. In this next section, we're going to learn about a different type of function called an exponential function that is actually necessary to accurately model real-world phenomena. I like to think of this as building our zoo of function types. So polynomials, rationals, and radicals are kind of like the cats and the dogs of the function world. They're the functions that most of us are most familiar with. And adding in exponential functions is adding in an animal that's a little bit more exotic. So maybe it's like a bunny or something. It's still not an extremely weird function. It's a typical type of function that you'd come across. You find it in applications all across the sciences and social sciences. You see it in engineering, you see it in economics, you see it in business. You can see it in areas that you wouldn't expect to find it. You can see it used in sociology for modeling populations, and in accounting and in finance. It's all over the place. And the form of it is very innocent looking. It's a function f of x that's equal to b to the power of x. And what's important is that the base, b, is constant, and the exponent is not constant. The exponent contains the variable x. We have some restrictions on the base. The base must be positive, so the base cannot equal a negative number. B must be greater than 0. And that's because we only want to work with real numbers. And if we go to a negative base, then we have to allow what's called imaginary numbers or complex numbers, and we don't want to do that right now. And the other restriction is not as important, but we'll adhere to it anyway. The base will not be equal to 1, because 1 to the power of x would be a fairly boring function to work with anyway. Okay, for the next, or for these 4 functions, x to the 3, 3 to the x, x to the 2, and 2 to the x, what I want to do is I want to evaluate them at just a selection of x values, just to get some practice with evaluating exponential functions and distinguishing them from polynomial functions that may resemble almost the same thing, but they're actually quite different. So I'm going to evaluate f at -1. So this is -1 to the power of 3. We replace the x by -1, and this means -1 multiplied by itself 3 times. So -1 times -1 times -1, which is -1. Okay, now we'll plug in 0. F of 0 is 0 to the 3. So 0 times 0 times 0, which is 0. F of 1 is 1 to the power of 3. So 1 times 1 times 1, which is 1. F of 2 is 2 to the power of 3, which is 2 times 2 times 2, which is 8. And then we have f of 3, which is 3 to the 3, 3 times 3 times 3, 27. We'll contrast that against 3 to the power of x, where what we're doing is we're just switching where the variable is and where the constant is. So instead of the constant being in the power, now the constant's in the base and the power contains the variable. So we will evaluate this at the same x values, f of -1, that's 3 to the power of -1, which, recall from our laws of exponents, or notation for exponents, this means the same thing as 1 over 3. And we can already see a big difference that for the first function, the one on the left, when we plugged in -1, we got -1. For the second function on the right, when we plugged in -1, we got 1/3. So very, very different. Okay, now 0, 3 to the power of 0, which is 1. Remember that anything, or almost anything to the power of 0 is 1. F of 1, 1 to the power, or 3 to the power of 1, almost messed that up, 3 to the power of 1, which is 3. F of 2, 3 to the power of 2, which is 3 times 3, which is 9. And the last one, f of 3, 3 to the 3, which is 3 times 3 times 3, which is 27. And that last one is the only one that matches. And it matches because the base and the exponent are both 3 in that case. So those functions are intersecting at that point. If we were to make a sketch, the function x to the power 3 and the function 3 to the power of x, they cross at that point. And maybe some other points as well. But that's a topic for a different day. Okay, let's do the next set. I'm going to plug in -1 into x power 2, which is -1 times -1, which is +1. I'm going to plug in 0, which is 0 to the power of 2, which is 0 times 0, which is 0. f of +1, 1 times 1, which is 1. f of +2, 2 to the power of 2, which is 4. And then f of 3, 2 to the power of 3, which is 2 times 2. Oh, sorry, 3 to the power of 2. Sorry about that. 3 to the power of 2. 3 times 3, which is 9. Okay, now we're going to do the same thing for 2 to the power of x. We're going to evaluate it at each of those x coordinates. So 2 to the power of -1, which from our rules for exponents means 1/2. We have f of 0, 2 to the power of 0, which is 1. Almost anything to 0 is 1. f of 1, we have 2 to the power of 1, which is 2. So far nothing matches. f of 2 is equal to 2 to the 2 equals equal to 4. Okay, there's the one that matches because both the numbers are the same, base and exponent. And f of 3, 2 to the power of 3 is 2 times 2 times 2, which is 8. So we can see that they're very different functions, x squared versus 2 to the x, just as x to the 3 and 3 to the x are different functions. Here's a graph of x to the 3 and x to the power of 2, and another graph of 3 to the x and 2 to the x. And what I'm going to do is I'm going to open up Desmos and graph them together. So Desmos.com, click on the calculator. I'm going to type in x to the power of 3 and 3 to the power of x. Put them side by side. You can tell that they're very different. And then I might as well also do x to the power of 2 and 2 to the x. I know it's a mess, but no, 2 to the x. Okay, 2 to the power of x. Okay. Now it's a bit of a mess, so maybe what I'll do is I'll make these ones. So the polynomials I'll keep as dotted and blue. And this one will do dotted in purple. And the other two I'll make red full line and orange full line, so it's a little bit easier to distinguish. Okay, so zooming in, I did something wrong. I didn't want to do that. I want these ones to be solid. It's not that it matters, it's just I want it to be easy to tell what's what. Okay, so that's that one red and full. And then, hey, don't do that yet. And then I want this one to be squared, dotted, and purple. Okay, done. So we have the polynomials are dotted curves, and the exponential functions are the solid curves. So you can see that the exponential functions both have this feature that on the left-hand side, their y value is very low. So for very negative x values, exponential functions are very small. And for large x values, these exponential functions, they grow very quickly. And if you zoom out far enough, you'll just see how quickly. Let's see if I can. It's going to take a while to zoom out far enough, so I'm going to cheat. I'm not going to zoom out. I'm going to change my scale. I'm going to go from, let's go from -1 to 500. Oh no, 500, let's go 50. Let's go 80. Okay. That's going to be hard to see. But eventually, these two solid curves, the exponential curves, are going to be far higher than the dotted curves, the polynomial curves, for all x values that exceed a certain point. So I'll turn this off. We don't need it for, we'll come back to pictures in a moment. What I want to do next is take a function 4 to the power of x and evaluate it at some different x values, including fractional values and some negatives. A lot of what we do with exponential functions is we explore their properties through evaluation, and that is going to require the use of the laws of exponents. So it's just some practice for doing that. So starting with f of -2, that's 4 to the -2, which is 1 over 4 to the positive 2 using our rule for negative powers. And then 4 squared is 16. We'll go to the next value, f of -1. That's 4 to the power of -1, which is just 1 over 4, nothing to do. F (-1/2). This is a tougher one. First thing is we deal with the negative part of the exponent. So I'm going to make this 1 over 4 to the positive 1/2. And then positive 1/2 means square root. So 1 over the square root of 4. And the square root of 4 is 2. Okay, now I'll move to f of 0. F of 0 is 4 to the 0, which is 1. And f of 1, which is 4 to the power of 1, which is 4. And now we'll do the next set up here. F of 1/2 is 4 to the power of 1/2, which I'll convert into square root of 4, which is 2. F of 2, which is 4 to the power of 2, which is 4 times 4, so 16. And the last one, we plug in 3 over 2. We're going to have a few more steps to do. 4 power 3 over 2. So remember, what does this mixed fraction mean when we have a top number that isn't 1 divided by a bottom number that isn't 1? What we can do is we can convert this into a square root of 4 all to the power of 3. Or if you want to do it in 2 steps, I can say this is 4 to the power of 1/2 all to the power of 3. We're unmultiplying the 3 over 2. We're writing it as 3 times 1 over 2, and then using the law of exponents, just using the law backwards. It says that a to the m all to the n is a to the m times n. We're writing that in reverse. Okay, now we can convert that into a square root. So we have square root of 4 all to the power of 3. So that's 2 to the power of 3, which is 8. So that last one is the hard one. That's the challenging one. We have to use several different exponential function notation shortcuts. Where do these things come up? So I mentioned already some broad areas where exponential functions are naturally show up. You don't have to force an exponential function to arrive. It arrives exactly where it should, where you need it. So a natural place where you need an exponential function is when you want to describe the growth of a population. If you have some initial population A, so let's say an island with 100 bunnies on it, and some growth rate K. So the time over which, or that K is related to how long it takes a population to double. So for bunnies, I don't know, can a bunny population double in 2 months? Maybe. I don't know enough to answer that. But whatever the case is, it has a doubling time. Then what you could do is you could write that the population as a function of time is equal to A, the initial population, times 2 to the power of kt. And you want to know, let's say, the population after 10 weeks, you replace t with 10, and that would tell you what that population is. Other models of population are more complicated. So that model that's at the top, A times 2 to the kt, that assumes that the population can grow without bound. It can grow forever. It's never going to run into a resource limitation. Like they're not going to run out of space, they're not going to run out of food, not going to run out of water. But no population grows like that for very long. Maybe initially a population can grow very quickly, but eventually it starts to level off. What's happening is that the population is feeling its carrying capacity. How able is the environment to support that population? So you start running out of food, you start running out of space. Now there's other things that can inhibit a population from growing exponentially forever. The model, I'm not going to read it, the model is given there. P of t is equal to the thing with the m in it. Both of these exponential models are things that can be derived from scratch. They can be derived from basic logic, and it's one of the exercises that is done inside Mathematics 1230 towards the end of the course. We derive these from what's called a differential equation. For most of the people inside this course at Mathematics 0110, where you will see exponential functions more likely or more prevalently is in finance, financial modeling. So let's say you have a pile of money, I'll call that pile of money P, and you're investing it for X compounding periods. So X might be a certain number of months or a certain number of years. The money is being operated on with an interest rate R. So an example, 4% interest rate, you'd have to convert that into decimal forms, so 4 divided by 100, which is 0.04. Then after X compounding periods, the value of that pile of money is going to be given by that formula P times 1 plus R to the power of X, where 1 plus R is the base of the exponential function. X is the exponent, and the P in front is just multiplying that function. It's a constant multiplied by the function. If your money is, let's say, compounded monthly instead of yearly, and your interest rate R is given annually, you can do some rearranging with units and come up with this formula. So this is just this is the same formula as above with different units, a different way of expressing the compounding period compared to the period of interest. So if you're interested in years, and the compounding period is in months, then you have to convert using a formula like this. And you'll come across this if you take any courses in finance, you take any courses in actuarial science. It's a very common formula. So right at the start, when you saw the word exponential functions, you should have immediately thought exponent laws. They are one and the same thing. That exponential functions are the functions that are ruled by those laws. So it should not come as a surprise that they're going to return in a really big way inside this part of the course. So just as a reminder of those laws of exponents, the first one says that if you have b to the x times b to the y, you get b to the x plus y. What's important is that the bases have to be the same. Also, if the bases are the same, then b to the x divided by b to the y is b to the x minus y. This next one we used in one of the examples today. B to the x to all to the power of y is b to the x times y. This next one we don't often use. A times b all to the x is a to the x times b to the x. We can distribute that power to both objects in a product. Or in a division, a over b all to the x, we can distribute that exponentiation to the top and the bottom separately. So we'll make use of these rules and more. We'll do some more things, but let's cut the video here and continue in video 2.